Alright, so let's do a Windows exploit. On the exploit development page, this is ED308. Students who go on and get the exploit development certification from the people that make OSCP have told me this is the most important project. And so there's a thing called Vulnerable Server that somebody wrote to practice people, to help people practice exploiting Windows, and there are quite a few steps. So you download this Vuln server and run it, and it then listens. I said, there we go. It listens on port 9999 on the Windows machine. Now there are a couple of adjustments to make to your Windows machine. If you have a client side of Windows, then I see good, Marwan. The client side of Windows, you're fine, but if you have a server, they've turned on data execution prevention in a more strict way. So this is the default for client machines. If you're using a server, you should set it there and then restart the machine. And it's sort of nice to enable error reporting in group policy, although not really necessary. So you can see an error message that's going to pop up pretty soon. And you have to turn off the firewall, or if you're a more cautious type, just open port 9999 to let the traffic in. And then you can run this thing called Vulnerable Server, and you can connect to it from a Linux machine, which is what I'm using Debian Linux as the attacker here. So I've SSH'd into my Linux machine, and I can connect to the Windows machine with Netcat on port 9999, and you see it shows me coming in, and now I can execute commands. If you do help, you see there's a series of commands here, and it has a variety of commands just sort of to look sort of like an email server, nonsense commands, and exit disconnects. And each one of these has different vulnerabilities to explore. The one we're going to do is Trun, which has a simple buffer overflow vulnerability, like the ones that we were exploiting on Linux. So I'm going to exit for now. That connection is just to make sure that the networking is right. And this is still running, you see. So now the first thing you have to do is fuzz it. Because we've done this before, you need to send traffic of variable length until you find out what length causes the overflow. So this connects to the server. Oh, I think I'm going to need to fix that address. Yep. So I better nano this. My machine is at 129. No, it's at 130, not 139. Okay. So I'll change that to 130. Other than that, I think we're okay. I input the length of an attack, and then I connect to the server, and I send that many capital A's, followed by carriage return line feed, preceded by trun space dot, which is the way this thing works. It expects that to start it. So I'll save this, and then Python, I think I can probably just run it with /. Yeah, okay. And it's going to ask me for links. Let's send 100 A's, and it works and says goodbye. It did not crash. So I'll send 1,000, and it still works. So I send 2,000, and now it crashes. And you see an error message appear here. And I can program stopped at work correctly. I can try debugging it and see what happens, but then it's going to start Visual Studio or something. I don't really want to do that. So anyway, that shows you it crashing. So 2,000 characters is enough to cause a crash. And so let's analyze these in this crash in a debugger. So what we're going to do, we're going to use the Immunity Debugger, which should be installed here. If not, I'm going to have to get it. I switched to Windows 11, and I may not have everything I usually have installed on this machine yet. I do have the Immunity Debugger. Oh, there it is, right there on my head. All right, so I can run this. This is very nice. And now I can open that file, file open, and go to my downloads, and Vuln server. Okay, now it's open in the debugger. which is going to load it and then pause. Now, this font is ridiculous. Let me spend a minute fixing that. Options, appearance, fonts. I'm going to take OEM fixed font and change it to be bigger. And then I'm going to switch everything to OEM fixed font. Appearance, fonts all, OEM fixed. All right, now we can see what we're doing. So in the debugger on the left, you see the code. Windows programs, Windows executables always load at 400,000, at least as a virtual address. And the text section that contains the assembly code starts at 401,000 typically. So these are the assembly code that makes up this program. Here are the registers like EAX and ESP and EBP, the stack pointer and the base pointer that we've seen before. This is 32-bit code. Here's an area where you can just dump any region of memory in hex to examine it. And this is the stack, which contains pointers to various objects. Right now it contains return pointers, so when I end the program, it can go to return to kernel 32, return to base thread, return to ntdil, and those are the steps it'll use to return back to Windows if I close the program. Now right now the program has loaded and it is not running. That's the way debuggers work. They load it and stop the program so you can examine it. It says paused in the corner. You have to run it here. Now it's running. Now I can send that attack that makes it crash again. So I run the fuzz and I send it 2000 A's. And it crashes. Now notice at the bottom there's a message telling me what the crash was. Access violation when writing to 41414141. Now 41 is hexadecimal for a capital A. So some of those 2000 letters I sent ended up in an address that was used for a write operation. Now you can take over the box with a write operation, but it's not the easiest way to take over a box. So I'm going to try and find a different crash. I'm going to restart the server with debug restart. Yes, it's going to reload it. And it's paused again, so I'm going to run it here so it's listening. And I'm going to try sending 3000. Because I mentioned before, you always want to keep the length of your attack the same when developing an exploit. And this is why 2000 bytes caused that crash, but 3000 bytes causes a different crash. Access violation when executing 41414141. This is much easier to exploit. Some of the capital A's I sent ended up in the instruction pointer, and it's trying to execute code at that address. So this is the easier one to exploit. You could also exploit the 2000 one, but we're going to work with the 3000 one. All right. So we've done that, and 3000. All right. So now what we need to do is create a non-repeating pattern of characters. So we can tell which of those 3000 characters ended up in there. And so I'm going to cat vseip0. All right, this is how I made a non-repeating pattern of characters. I made loops where I go 0, 1, 2, 3, 4, and then 2 loops that go from 0 to 9, and then just print them out. So it will print a capital A. So it'll just print a lot of numbers and then an A. So if I run this one, that's what it does. 000A, 001A, 002A. So if I get any 4 of these bytes in a row, I'll be able to tell which one it is. And now I want to send that to the server as part of the attack. So that's this one. This one will prepare the same connection. I'm going to have to fix that IP address. Then send 1000 capital A's, and then send that non-repeating set of 2000 characters here, so the total length stays 3000, and I can see what ended up in the instruction pointer. So I'm going to edit this one, which is vseip1. I need to make this 130. I think it's 130. Let's see. Yeah, it is 130. All right. All right. And so I want to run this again in the debugger so I can tell what happens. debug, restart. It reloads and pauses. Then I run it. Okay. Now I run VSEIP1. Okay, so it sent 3,000, and here it access violation when executing 35, 32, 41, 31. So I've got that's 52A1. Just what you see here. And so that's here. It's backwards, 52A1. That's where it is. So that is, it turns out, 1006 into this thing. You can figure it out. And so we can now target the EIP precisely. Now I know how many characters in it is the character that ends up in it. So that's VSEIP2. I need to change this address. All right. And so you have to send 2006 capital A's to get in. Then I'm going to send BCDE, intending for that to hit the instruction pointer. Then I'm going to put padding, which is enough F's after that to make the total length stay at 3,000, because I really need to keep that length fixed, so I keep on hitting the same crash. And that's it. So if I did this correctly, it'll put a BCDE in the instruction pointer. So let's try that. Restart this thing in the debugger. And it starts out paused, so I run it. Now it's listening. Now I send that VSEIP2. And there we go. Access violation when executing 45, 44, 43, 42. And that is a capital BCDE. So it worked. I now have precise control of the instruction pointer. Now I can do an overflow and I can run code to the instruction pointer. So let's see what memory. Now I have to figure out where the ESP is. If you look up here, here's the ESP, and here's what it's pointing to, FFFF, right? So some of the F's are what the stack pointer is pointing to. Now this is important because remember we turned off address space layout randomization on Linux. You cannot turn it off on Windows. So you're not going to be able to feed in an absolute address anywhere because you don't know where you are in memory. So we're going to have to use a trampoline attack where we bounce off another command and come back, and we're eventually going to execute code at the ESP. So I need to know what's at the ESP and do I control it. So if I click on the ESP address, right click and follow in dump, I can see it's F's, and if I scroll up a little, I can see it's the first F. So here's all the A's I injected, here's the EIP I injected, BCDE, and at this point the stack pointer points right to the next byte here. So if I can find a way to jump to the stack pointer, I'll be able to hit the code that I injected right there, and that's how we're going to defeat address space layout randomization. So we now know we can control the instruction pointer, and we have a place to put the attack. The only problem is there are certain characters you can't use. If you remember before, things like spaces and tabs and carriage returns and line feeds and null bytes tend to break code. So it will break the string, and so you might expect those things to make trouble. And so to test that, we have to make an attack that's going to send possible bad characters. So that is a VS bad characters. All right. Oops, that didn't work. It's bad char 1, okay? All right. So I got to fix the address. All right, and what this is going to do is it's going to, from 0 to 256, it's going to add this to test characters and send it to the server. So a total of 256 characters, but but it's going to send it in the same format, a total of 3,000 characters, but those 256 characters being sent right after the BCDE, over here where the F's are, so I can see if they get there. So I'm going to restart the server, debug, restart, yes, wait for it to load, Now run it so it's listening. Now I run the bad character script. All right, and so it passed the BCDE, and here's the stack pointer. Notice there's no characters here. That's disturbing. If I follow in dump, there's nothing there. No 0, 1, 2, 3, 4, because the null byte, the 0, terminated the string, and everything after that was ignored. So I learned nothing terribly exciting here. I learned that null byte is a forbidden character. So let's try again. But the next one, I'm going to remove the null byte. So let's nano vs bad character 2. All right, this one, let me fix the IP address. Okay, this time I'm only going to go from 1 to 256. I'm not going to try sending a null byte. I'll send the other characters. So restart it here, debug, restart, yes, and run. And now I send that one. All right, now stack pointer still shows nothing. I still crashed at BCDE, so this is fine. But if I look at what's at the stack pointer, some of it got there. 1, 2, 3, 4, 5. It's not printable. It made it up to 10. In fact, it looks like it all got there. 8, 10, 20, 30, 40, 50, 60, 70, 80, 90, A0, right up to FF. So all the other characters are okay. The only thing forbidden is a null byte in this program, so that's very handy. All right. Now, so we know what characters we can inject, and we know how to control the EIP. The problem is the instruction pointer. We need to find code that does not move, that does not have address space layout randomization, and for that there's a Python module called Mona that you can add in here. And so if I do bang Mona, you have to download it and drag it into a folder, but I think I've already done that. Yes, I have already done that. And let me see if I can get the font to look better here. Appearance, font, OEM fixed. All right, this is the help message for Mona, but I don't need that. What I want to do, I'm going to run it here with just Mona modules. Bang Mona modules. This is going to show you the modules used by the current program, and it's going to show you what protections they have. And I'd like to scroll horizontally, but I'm not sure I can. Oh, I can. Good, with the mouse. All right. So if you go over here, you see the modules. Here is the Vuln server itself, and here is the libraries used, essentialfunctions.dil, and then here's your Windows libraries, kernel base, MSV, CRT, NTDIL, and so on. And here are the defenses. Address space layout randomization is the most important one, and as you can see, it's turned on for all the Windows built-in modules, but it's turned off for Vuln server and ESS Func, because they compiled this using the switches in Visual Studio, or an old version of Visual Studio that didn't enforce this. This, by the way, is one of the reasons why you don't want to run old code. Old code typically cannot have all the newest defenses unless you recompile it with a more modern version of the compiler. So in this particular old code doesn't randomize. So there appear to be two places where we can find some code to use in our exploit that won't move, but there's really only one, because you have to look at where it is. The two modules without address space layout randomization are the first and the third one. And the first one, look at the third one. Third one is the executable. And this is what I told you. Windows executables always load at 400,000 in hex. So every address starts with a null byte, 00. So I can't use any of these addresses because the null bytes in them will stop the string. But the library has loaded here at 6250, and there are a bunch of addresses inside there that won't contain null bytes. So I can use instructions in essfunc.dil. Now what I need to do is find a jump ESP. I want to find code in Mona that will jump to the stack pointer. And for that, I can use this command, Mona jump -r ESP in module essfunc.dil. this hunts through that module to find commands that fit that, and it had a minor bug. It didn't go to the right window, but the one I want to look at is the log window. All right, here it is. And I got to scroll to the left to see it. There are a total of 9 places in that module that contain a jump ESP command. So I could use any of these addresses. They will always be the same. They will not randomize. And if I jump to one of these addresses, it will then come back and jump to the ESP. So now I have almost everything I need. So we can test code execution. Let's try nano VS EIP3. All right, so I'm going to fix the IP address of the server. And here I have the same thing as before, 2006 A's to get to the sweet spot where the EIP is. Now I put in this address, 6250.11AF backwards, 6250.11AF. Now I make my dummy exploit, 16 bytes of NOP sled, which is 90, and then a break, which is CC, and then enough padding, F's, to make the total length 3000. So if this works, it will put this in the instruction pointer, jump to some jump.esp, come back, jump into the NOP sled, execute 16 bytes of NOP sled, and then hit the break. So that's my dummy exploit to test if I really have control of the instruction pointer and I can execute code I've injected. So I save this and restart my vulnerable server. And run it again. And run VS EIP3. All right. Now it hit an int3 command here, and that's because I put it here deliberately. DC, if I go here, I want to scroll up a little. There we go. So there you are. It slid down the NOPs. And this is that address, 6250.11AF. It bounced off of that, hit the NOPs, slid down the NOPs, and hit the int3. So this proves I'm able to execute code in this location, and I'm able to reach it and execute it despite address space layout randomization. So now it's just a matter of generating an attack, and you do that again with Metasploit. So MSF Venom can make it, and you can choose a Windows attack. This is one of them, Windows Meterpreter Reverse TCP, where it'll phone home. I'm going to have to regenerate it, so that's a good thing to do anyway. I'm going to have to regenerate it to get to the right IP address of my control server here. So I'm going to get the IP address of this server, which is this one, and 123 ending in 129. All right, here's the Metasploit command that creates the malware. There. Now I got to fix that address to be 129. Okay, so this is going to do a reverse TCP, which is usually what you want on Windows, because the Windows firewall blocks unexpected incoming connections, but it doesn't block outgoing connections. So when you run malware, you want it to call out, which I remember I mentioned when we did the Splunk. This is why you should not allow your server to make any outgoing connections. We're going to make this attack. This Windows server is going to make an outgoing connection to my command and control server, and I have to tell it the address. That's the reverse TCP part. Here's the address of the command and control server, and here I tell it not to put in any null bytes. That's a bad byte. Don't use it. And expect to contact my server on port 443, so it will look like an HTTPS connection and presumably not be blocked by the firewall at the company I'm attacking. So that's the command that generates the Python code I need. All right, I'm going to copy that code. It's quite a bit bigger than the code we generated for the simple Linux attacks. And now I'm going to put that in VS Shell. I got a couple adjustments to make to this shellcode. The first thing is I want to fix this server address. And the next thing is I want to use the new stuff I just copied instead of this old exploit that had the wrong command and control IP address embedded in it. So I'm getting rid of the old stuff. Okay. There. So it's the same story as before. I have 2006 A's. Then I have the 6250 11AF, which is going to be a jump ESP. And all the rest ESP will start here. I have 16 bytes of NOPSLED. Then I have this Metasploit generated payload. And I just add enough F's at the end to make the total length 3000 and send that. So I'll save this. And now I'm going to need to start a listener. So I'm going to need a second terminal window on my Linux machine. All right. A second SSH window in, I should say. And this is going to be Debian at 172.16.123.129. Okay. So I start I need sudo because I need to listen on a privileged port of 443. MSF console, and I'll make it quiet so it doesn't print a big annoying banner. Okay, I tell it to handle incoming data, and should have pasted, there it comes. Set the payload to the Meterpreter reverse TCP, set the port to 443, and run the exploit. All right, now it's listening for traffic coming in from the Windows target. Now I restart this, debug, restart. And run it so it's listening. And now I send that in, VS shell. And there it goes, it worked. You see it's already communicated with my command and control center here, and here it comes. Now I have a Meterpreter session open, and so I can do things like help to see the Meterpreter commands. This is a Trojan that's used to remote control Windows PCs. It gives you a lot of options here. Execute commands, get environment variables. You have netstat, you have ARP, you have route. You can download and upload files. This is a handy piece of malware that gives you a lot of things you can do on the server. And I think you can do sysinfo. Yeah, and that tells me I'm exploiting Windows 10, although this is in fact Windows 11, so that's a little rude. But anyway, I am in control of Windows machines. I wonder if I have who am I? I think I might not. I don't have that command. All right, so anyway, that's the exploit, taking over a Windows machine with Meterpreter and exploiting a buffer overflow. So I'm going to stop this video.